A discrete probability function is defined as shown here. We can see that there's an unknown p, which is appearing in the table. We want to find the value of p. We know that the probabilities must all add up to 1. Now the ones that we can actually see are 0.1 and 0.1. So add those and we get 0.2. And then we've got p, 2p, 4p. So that's got to be equal to 1. So 4p is equal to 0.8, making p equal to 0.2. So if we replace the p's in the table here, we would have 0.2, 0.4, 0.2. And essentially we've done part D, but I'll come back to that shortly. We now want to state the probability that x is equal to 3, and we can just read that from the table. That is 0.4. State the probability x is more than 2. Now for a discrete distribution, that's the same as saying more than or equal to 3. So it's the probability that x is equal to 3 added to the probability that x is equal to 4, added to the probability that x is equal to 5. So that is going to be equal to 0.4, add 0.2, add 0.1, so that's 0.7. Now, finally, we said we'd come back to this, and obviously the table is a completely valid way of doing that, and drawing a graph is a completely valid way of doing it. Can we state it nicely just as a function? Well, we can, and the fact that this goes up 0.1, 0.2, 0.4 suggested to me that I might do something like 0.1 times 2 to the x minus 1 for x belonging to 1, 2, and 3. So for example, when it's 3, we've got 2 squared, which is 4, times 0.1, which is 0.4. And then we could have 0.1 times 2 to the 5 minus x if x belongs to 4 and 5, and 0 otherwise.